the lungs, these simply exchange. Yes, but not quite that easily. It has to be controlled. So, this is what I was talking about for the P that you may see. You may see in your reading, lab, and so forth, something such as the P and then O2, P, CO2, that sort of thing. This means the partial pressure of this gas. It can be referred to as being in the capillary, in the blood, or in the alveoli. Just letting us know that we're going to have amounts that are present. And then if you just add them up, they become the total. Your textbook's going to get into great detail because it's going to talk about how we have to pay attention to altitude. Like, for example, for the most part, we're pretty much at sea level. Okay? So, we're at 1 torr.
But with the partial pressure, just because one gas may have a higher pressure doesn't necessarily mean that there's more of that gas, right? Due to the mass of the molecule, right? And so is that where Henry's law comes into play with like the Henry's gas, with the Henry constant, because each constant is different?
Because each one of these gases is going to have a solubility component.
Yeah, that's the Henry's.
And that's Henry's.
Yeah.
Okay? So, right, you could have a different P, partial, in the blood versus the alveoli, and movement is going to be based on their solubility in the water of the respiratory membrane. One of these gases dissolves more easily than the other. Can you guess which one dissolves more easily?
Oxygen.
Do what, Molly? Carbon dioxide. What? Yeah. Wait a minute. All this time that you've been taking science classes, all this time that you've probably been alive, it's always been oxygen, 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 oxygen. Correct? No. Guess what controls? CO2. Yes. CO2 is the controlling factor in how the gases are going to move. So, in an alveoli, we come into contact with a film of water between the alveoli and the capillary. Oxygen needs to dissolve in this water to cross into the capillary. Is everybody with me? To get it into the blood, okay, we need to make sure that it dissolves in that water. But wait a minute, I just told you that it doesn't dissolve easily. CO2 dissolves more easily. Carbon dioxide is going to dissolve easily, make its way to the alveoli and out of the body. Because CO2 is toxic. all right? But the oxygen that will get exchanged will be dependent upon the metabolic needs of the body. If the body is not active, oxygen demand is low. Meaning, if you're just sitting there like this all day, that's not a high demand for oxygen. CO2 is still getting made, not in high amounts, but oxygen, I don't need to pick it up every single time the red blood cell makes it through the pulmonary circuit. Because the red blood cell will hold on to the oxygen. The red blood cell has hemoglobin and will hold on to the oxygen. If the tissues of the body do not need it, it doesn't drop it off. So, at a constant temperature, i.e. 98.6, at a constant temperature, the amount of a given gas dissolved in a given type and volume of liquid is proportional to the partial pressures. What we're going to say, at the alveolus, blood unloads the CO2 and loads O2. Pressure gradients will affect this. For example, right now, we are at atmospheric pressure, 1 atmospheric pressure. We're at sea level, okay? But if you were to go to a higher altitude that is way above sea level, you've got more pressure. The body needs to meet that demand. Air, not as great, and it's got to adjust to that altitude. Your area that you will live will affect your breathing. Why do you think it affects cooking? Why do you think when you buy a cake mix and you go to fix it, it will have on the box somewhere, if you're above this amount of sea level, cook it at this temperature?
But a pressure is directly proportionate to the boiling temperature of fluids and things like that.
Yes.
So if you go to a higher pressure, then it'll cook faster, I think, right?
It will cook faster, so they usually tell you to put it at a lower temperature. Yeah. So where we might cook that cake on the cake mix at 350, go to a higher altitude, they'll say cook it at 325. Yeah. Bread making, for example. The higher in elevation you go, the P's, the partial pressures of the gases, are lower. For example, your oxygen would be lower. So if we went to Denver, oxygen level in our blood would decrease. We would begin to feel that little bit of dizziness and short of breath and so forth. And it takes you probably about 3 to 5 days to acclimate. If you go there for a trip that's only 3 to 5 days, when you come back, you should be very energetic because your body has made more red blood cells, and you come back here to sea level, and they're all available, and they're going to be flying around for 7 to 10 days. So, actually, makes you more energetic. So, for Henry's law, Henry is going to tell us that these movement of gases are going to get affected based upon respiratory membrane, the thickness, the amount of water. What we need to do, oxygen, CO2. One of the things that will happen, like I said, oxygen bound to hemoglobin. If you go back and look at that hemoglobin molecule, does everybody remember that hemoglobin molecule? All right. And we had 4 heme groups. Does everybody remember that? And if they had the iron, 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 each one could attach 1 oxygen molecule. So, if each one on this 1 hemoglobin could attach an oxygen, it would be 100% saturated. Meaning, that 1 hemoglobin and that 1 red blood cell was carrying all 4 possible oxygens. As it makes its way through my systemic circuit, is everybody following me? Okay? And if you were really active, chances are it would drop off, all 4. And as it returns to the heart and begins the pulmonary circuit, how much do you think it would want to pick up? If it had no more oxygens when it returned to the pulmonary circuit, how many oxygens do you think it would want to pick up in the lungs?
4.
It would, because it could, pick up to 4. They usually pick up, if they're completely depleted, okay, they will pick up between 3 to 4 oxygens. Now, do you guys remember how in this hemoglobin, these are my protein chains, okay? And the protein chains could pick up CO2 if they need to, but they don't want to. They would rather, for that CO2 that's getting picked up on the systemic circuit in the blood, okay, they would rather buffer the CO2. Is everybody following me? Okay. All right. If we think about our bloodstream, because what's going to happen, blood leaves the heart. When it leaves the heart, and let's think about only 1 red blood cell. And let's think about only 1 hemoglobin. Okay? And let's say that that red blood cell with that 1 hemoglobin had all 4 oxygens. Okay? As it makes the circuit through the systems of the body, let's say it drops off